planet spins in darkness, wrapped in an atmosphere that would kill anything alive today. There is no green, no breath, no lungs to fill. The air that moves across the young continents carries no oxygen, only the exhalations of a cooling world, nitrogen, carbon dioxide, methane, water vapour. It rises from countless volcanic vents, seeps through cracks in fresh basalt, drifts across oceans that have just begun to settle into their basins. This is the Archean Eon, more than 2.5 billion years before the present, and the sky holds nothing that could rust iron or sustain fire. The atmosphere builds itself slowly, molecule by molecule, from the interior of the Earth. Magma reaches the surface and releases its trapped gases. Steam becomes cloud, cloud becomes rain. Rain falls on stone that has never known rain before, and the cycle begins to turn. There is no plan to this, no intention. The planet is simply cooling, outgassing, rearranging its chemistry according to pressure and temperature and time. The air thickens, the pressure at the surface rises, and still there is no oxygen, not a single molecule free in the wind. What the sky does contain is methane, great quantities of it, possibly produced by early microbes, possibly seeping from geological processes that remain debated among scholars. The methane acts as a greenhouse gas, holding warmth close to the surface, keeping the oceans liquid despite a sun that burns 20 to 30% dimmer than it does today. Without this methane, the planet might freeze. With it, the temperature hovers in a narrow band, allowing water to pool, allowing chemistry to continue its experiments in tidal zones and shallow seas. The atmosphere, in this sense, is a blanket woven from volcanic breath and microbial waste. Protective, accidental, essential. The young Earth knows nothing of oxygen's absence. There is no comparison to make, no memory of the different air. The stone does not corrode. The iron that lies exposed in mountain slopes and riverbeds remains grey and unreactive, sleeping in a chemistry that permits it to stay reduced, neutral, waiting. In shallow pools where water evaporates under the faint sun, minerals precipitate in patterns that will one day fossilize into rock. But these minerals tell no story of rust, no tale of oxidation. They speak only of a world balanced in its own peculiar way, stable in its oxygen-free equilibrium. The absence of oxygen means other things, too. It means the upper atmosphere lacks ozone, that thin layer of 3 bonded oxygen molecules that will one day absorb ultraviolet radiation and make the land surface habitable. In the Archean, ultraviolet light pours through the sky unfiltered, striking the ocean surface, penetrating the upper meters of water. Life, if it exists at this time, and it does, in microbial form, must stay deep or hide beneath mats of its own making, shielded by layers of mucus and mineral. The land is sterile, baked under radiation, inhospitable to anything living. Only the ocean offers refuge, and only its depths offer safety. Scientists studying this ancient atmosphere look for clues in the rock record, isotopes of sulfur that fractionate in ways only possible without oxygen, minerals that form only in reducing conditions, the absence of red beds and oxidized soils. They find what they expect, a world chemically distinct from the one that comes later, a world where iron moves freely through water, where methane drifts thick in the air, where the sky itself would appear a different colour to any eye that could see it. Perhaps a hazy orange, perhaps a pale grey. The exact hue remains unknown, a detail lost to time, guessed at through models and analogy. And yet, even in this alien air, the chemistry of life is stirring somewhere in the warm shallows, or near deep-sea hydrothermal vents, or in tidal pools along ancient coastlines. Microorganisms are evolving. They metabolize hydrogen, they reduce sulfur, they ferment simple organic molecules, They split water to harvest electrons, though most do not yet release oxygen when they do so. They're inventing biochemistry, trial by trial, across millions of years, in a slow groping toward complexity. Most of what they invent will fail. Some will persist, and one particular invention, not yet common, not yet widespread, will eventually change everything. The planet does not hurry. There is no deadline, no clock counting down to transformation. The atmosphere remains stable for hundreds of millions of years, perhaps longer. Methane continues to warm the surface. Carbon dioxide dissolves in rain and weathers rock, cycling through ocean and air in rhythms that will be recognizable even billions of years later. The nitrogen, inert and patient, makes up the bulk of the atmosphere then, as it does now, a passive backdrop to whatever chemistry unfolds around it. And oxygen remains absent, locked away in water molecules and metal oxides, not yet free, not yet transforming stone into rust or enabling the evolution of breath. Geologists sometimes call this the boring billion, though that term more accurately describes a later period. The Archean is anything but boring. It is the time when continents first begin to stabilize, when the oldest cratons form, when life establishes its foothold and begins to diversify in ways that leave only the faintest traces. It is boring only in the sense that it is slow, that its dramas unfold over timescales incomprehensible to human experience, that nothing happens quickly enough to make a sound. The wind moves across the water, the volcanic islands steam, the crust thickens, the mantle convects, and the atmosphere, hanging above it all, simply is, neither good nor bad, neither hostile nor welcoming, just the specific mix of gases that a planet of this size, at this distance from this star, can hold at this moment in its cooling. It will not stay this way forever, but for now, for a span of time longer than most mountain ranges will ever stand, the air remains unbreathable. The iron stays grey, and the world waits in its peculiar balance. Only later, much later, will oxygen begin to leak into this stillness, one molecule at a time, until the chemistry tips and the entire system reorganizes itself around a new element. But that transformation has not yet begun. The cyanobacteria that will trigger it are still rare, still evolving, still perfecting the molecular machinery that will split water and release oxygen as waste. They're practicing in the shallows, building their stromatolites, layering sediment and slime in structures that will fossilize and endure. They're preparing, without knowing it, to poison the world. The ocean does not arrive all at once. It condenses from the sky over millions of years, one rainstorm at a time, filling the lowest places first, the deep fractures in the crust, the basins formed by subsidence and early tectonic motion, the vast depressions that will one day be called ocean floors. The rain falls hot at first, almost steam, striking stone that radiates heat back into the atmosphere. The water evaporates, rises, cools, falls again. This cycle repeats, each iteration slightly cooler than the last, until finally the surface temperature drops below the boiling point and water begins to accumulate. There is no witness to this. No eye watches the first permanent puddle form, the first tide pool that does not evaporate by noon, the first shallow sea that stretches beyond any visible horizon. The planet makes its ocean in silence, drop by drop, century by century, while the sky slowly clears of its densest steam and the volcanic outgassing continues its work. Some of the water comes from comets, delivered by impacts during the late heavy bombardment, but most simply rises from the interior, water that was always there, trapped in minerals, released by heat and pressure as the mantle churns and the crust fractures and the young earth reorganizes itself. The first ocean is not salty yet, or not as salty as it will become. The sodium and chloride that will define seawater are still locked in minerals on land, waiting to be weathered out by rain and carried to the sea by rivers that do not yet flow. The water tastes of iron, perhaps dissolved from the basalt it pools upon. It tastes of sulfur, leaching from hydrothermal vents. It tastes of minerals that have no name because they exist only in conditions long vanished. Minerals that form in the absence of oxygen, that dissolve when oxygen appears, that will never be found except as faint traces in the oldest rocks. The ocean settles into its basin and begins to stratify. The surface layer warms under the dim sun, absorbing what heat the star provides. The deeper layers remain cooler, denser, less inclined to mix. Currents form, driven by wind and the planet's rotation and subtle differences in temperature. Water moves in great loops, spiraling through the basin, stirring nutrients upward from the depths, carrying dissolved gases from the atmosphere down into the interior. The circulation is sluggish compared to modern oceans, but it is there, turning, redistributing chemistry across vast distances. Near the shorelines, if shoreline is even the right word for the boundary between water and stone in this era, the waves lap at fresh volcanic rock. There are no beaches yet, no sand in the familiar sense. The continents are small, scattered, not yet assembled into the configurations that will be named Gondwana or Laurasia or Pangaea. They are protocontinents, fragments of stable crust surrounded by ocean, rising just high enough above sea level to shed sediment into the water. The waves erode them slowly, grain by grain, and the sediment drifts outward, settling in layers that will one day become shale. Sandstone, evidence of an ocean that covered most of the planet. The depth of this early ocean is uncertain. Some models suggest it was deeper than the modern ocean, with less land exposed and more of the crust submerged. Other models propose a shallower sea, with larger land masses than currently estimated, though still far smaller than the continents today. The truth is somewhere in the evidence, in the ratio of certain isotopes, in the types of rocks that form, in the distribution of sediments that manage to survive metamorphism and subduction. The ocean was deep enough to matter, wide enough to dominate the planet's surface, and persistent enough to stay liquid for billions of years despite a faint sun and an atmosphere that would shift and change around it. Beneath the surface, in the deeper layers where light does not penetrate, the water holds secrets. Dissolved iron saturates the ocean at concentrations impossible in modern seas. Kept in solution by the absence of oxygen, ferrous iron, the reduced form, the form that does not precipitate easily, drifts through the water column in quantities measured in parts per million, colourless, invisible, waiting. The iron comes from hydrothermal vents, from the weathering of basalt, from volcanic input along mid-ocean ridges that are just beginning to form. It accumulates over time, building towards a concentration that will one day matter very much. The ocean chemistry is alien. The pH is different, possibly more acidic, though this too is debated. The ratio of dissolved gases does not match anything in the modern world. Carbon dioxide dissolves readily, forming carbonic acid, lowering the pH further, affecting which minerals can precipitate and which remain dissolved. Methane bubbles up from the seafloor, either from geological sources or from methanogenic microbes that have colonized the sediments. The methane rises through the water column, some of it escaping into the atmosphere, some of it consumed by other microbes that have learned to metabolize it. The ocean is a chemical reactor, constantly processing inputs, constantly adjusting its balance, and in this reactor, life begins to spread. The earliest microbes likely emerge near hydrothermal vents, where chemical energy is abundant and the conditions are stable. They metabolize hydrogen and sulfur, drawing energy from the disequilibrium between the hot vent fluids and the cold seawater. From there, they disperse, carried by currents, drifting into shallower water, colonizing new niches as they evolve new metabolisms. Some learn to harvest energy from sunlight, using pigments to capture photons and drive chemical reactions. These early photosynthesizers do not produce oxygen. They split hydrogen sulfide instead of water, releasing sulfur as waste. turning the shallows faintly yellow-green with precipitated minerals. The ocean is not empty, then, but neither is it crowded. Life exists in pockets, in favourable conditions, clinging to rocks or floating in mats near the surface. It is entirely microbial, entirely single-celled, entirely invisible to any casual glance. A human standing on the shore of this ancient ocean would see only water, grey or green or brown, depending on the minerals suspended in it, depending on the angle of the light. They would not see the billions of cells floating just beneath the surface. The stromatolite reefs building themselves in the shallows, the invisible machinery of evolution experimenting with chemistry. The temperature of the ocean is another point of uncertainty. Some models suggest it was warmer than today, possibly as warm as 30 or 40 degrees Celsius in the surface layers, kept heated by the greenhouse effect of methane and carbon dioxide. Other models propose cooler temperatures, closer to modern tropical seas, with the warmth distributed unevenly depending on latitude and ocean currents. The evidence is sparse. Oxygen isotopes in ancient rocks, the types of minerals that precipitate, the distribution of stromatolites that seem to prefer warm, shallow water. The ocean was warm enough for life, cool enough to stay liquid, and stable enough to persist. The ocean also absorbs impacts. During the late heavy bombardment, asteroids and comets strike the surface with regularity, vaporizing water, throwing steam back into the atmosphere, creating temporary holes in the ocean that refill over time. Each large impact sterilizes a portion of the surface, boiling away microbes, resetting the local chemistry. But the ocean is vast, and life is resilient, and the impacts eventually slow. The water settles back into its basin, the steam recondenses, and the slow accumulation of dissolved iron continues, uninterrupted by catastrophe. Somewhere in this ocean, a new form of photosynthesis is evolving. It is not yet widespread, not yet common, but it is being invented, a metabolic pathway that splits water molecules instead of hydrogen sulfide, that uses the electrons from water to fix carbon, that releases molecular oxygen as waste. The organism that evolves this pathway does not benefit from the oxygen. The oxygen is poison, reactive, dangerous. But the organism benefits from the ability to use water as an electron source, because water is everywhere, abundant, unlimited, and so the mutation persists, the pathway spreads, and oxygen begins to leak into the ocean in tiny, negligible amounts. The ocean does not notice. The iron dissolved in the water reacts with the oxygen immediately, precipitating out as rust, falling to the seafloor as fine particles of iron oxide. The oxygen never reaches the atmosphere. Not yet. It is consumed as fast as it is produced, locked into minerals, buried in sediment. The ocean remains anoxic, reducing, hospitable to the microbes that have evolved in its depths. But the chemistry has shifted, just slightly, and the slow clock of planetary transformation has begun to tick. The water moves, the waves turn, the tides rise and fall under a closer moon. And the ocean, patient and vast, holds its dissolved iron and waits. The iron drifts through the water, invisible and patient. It exists as ferrous iron, Fe2+, the reduced state, the form that dissolves easily in the absence of oxygen. In modern oceans, iron precipitates almost immediately upon contact with oxygenated water, rusting into insoluble particles that sink or remain suspended only briefly before settling. But in the Archean Ocean, there is no oxygen to speak of, and so the iron simply dissolves, accumulating over millions of years until the deep ocean becomes a dilute solution of metal, waiting for a chemistry that has not yet arrived. The concentration is substantial. Estimates suggest tens to hundreds of parts per million, levels that would make the water faintly cloudy if the iron were visible. Though ferrous iron in solution is largely colourless, the metal comes from everywhere, from hydrothermal vents pumping hot, mineral-rich fluids into the cold abyssal water, from the weathering of fresh basaltic crust along coastlines. from volcanic input at mid-ocean ridges where new seafloor spreads and cools. The iron enters the ocean and stays there, dissolved, mobile, cycling through the water column in currents that move it from vent to shallows to deep basin and back again. This dissolved iron represents a vast reservoir of reactive metal, stored in liquid form, waiting. It's one of the defining features of the Archean Ocean, one of the chemical signatures that distinguishes this era from everything that comes after. In a sense, the ocean is a battery charged with reduced iron, holding potential energy in the form of electrons that have not yet been stripped away. When oxygen finally arrives, those electrons will be taken, the iron will oxidize, and the energy will be released in the slow, silent rusting of an entire ocean. But that has not happened yet. The iron drifts, unreactive, chemically neutral in an ocean that matches its chemistry. There is no urgency to this, no tension. The iron has been accumulating for hundreds of millions of years already, and it will continue to accumulate for hundreds of millions more. Geological processes are patient. The mantle convects on timescales of tens of millions of years. The ocean mixes on timescales of thousands, and the iron dissolved in the water simply is, neither building toward anything nor decaying away, just present, abundant, waiting for conditions to change. Near the surface, in the photic zone where sunlight penetrates, the first cyanobacteria are beginning to multiply. They are not yet dominant, not yet the primary architects of ocean chemistry, but they are there, building stromatolites in shallow bays, forming microbial mats in intertidal zones, slowly perfecting the biochemistry of oxygenic photosynthesis. They split water molecules, harvest the electrons, fix carbon dioxide into sugars, and release molecular oxygen as a byproduct. The oxygen bubbles up from the mats, rises through the water, and immediately encounters the dissolved iron. The reaction is swift and inevitable. Oxygen oxidizes ferrous iron to ferric iron, Fe3+, which is far less soluble. The ferric iron precipitates almost instantly, forming tiny particles of iron oxide that drift downward through the water column. The particles are small, often microscopic, rust red or rust brown depending on their exact mineralogy. They settle slowly, taking days or weeks to reach the seafloor, and during that descent they clump together, aggregate with other particles, form larger flakes that fall more quickly. Eventually they land on the bottom, accumulating in layers, building sediment that will one day become rock. This is the beginning of the banded iron formations, the BIFs, some of the most distinctive and economically important rock formations in the geological record. They form only in this narrow window of Earth history, only when the ocean holds both dissolved iron and a source of oxygen, only before the atmosphere itself becomes oxygenated and the iron supply runs out. The bands represent cycles, periods when oxygen production increases and iron precipitates rapidly, alternating with periods when oxygen production slows or iron input decreases, allowing other sediments to settle. The result is a layered rock, stripes of red iron oxide alternating with black chert or grey shale, a visual record of the ocean's chemistry written in stone. The formation of these deposits is maddeningly slow. Each layer might represent hundreds or thousands of years of sedimentation. Each band of red iron oxide might be only a few millimeters thick, the product of countless microbial colonies producing oxygen season after season, decade after decade, as the iron in the local water column gradually oxidizes and falls. The process is not linear. There are reversals, interruptions, periods when the ocean chemistry shifts and iron stops precipitating, or when the oxygen-producing microbes die back and the water returns temporarily to anoxic conditions. The bands record all of this, each stripe a snapshot of chemistry, each boundary between red and black a transition in the state of the ocean. Scientists studying these rocks find them maddeningly informative and maddeningly incomplete. The banded iron formations tell the story of oxygen's arrival, but they do not tell it simply. The bands are not evenly spaced. The chemistry is not consistent. Some formations show evidence of seasonal cycles, others of longer-term fluctuations in iron or oxygen supply. Some contain trace elements, rare earth elements, isotopes of molybdenum or chromium that hint at the chemical conditions under which they formed, but the details are often ambiguous, the interpretations contested, the timelines stretched across hundreds of millions of years with only scattered data points to mark the way. What is clear is that the iron acts as a buffer, a sink for oxygen. Every molecule of oxygen produced by cyanobacteria reacts with dissolved iron before it can escape into the atmosphere. The ocean holds an enormous quantity of iron, enough to consume the oxygen output of early photosynthesis for millions of years. As long as dissolved iron remains abundant, oxygen cannot accumulate in the water column, cannot reach the surface, cannot diffuse into the air. The iron, in a sense, protects the atmosphere from oxygen, maintains the reducing conditions that have persisted since the planet's formation, delays the inevitable transformation. And the iron does this without intention, without agency. It is simply metal dissolved in water, obeying the laws of chemistry, reacting when it encounters an oxidant, precipitating when it changes state. There is no plan, no strategy. The buffering effect is a side consequence of abundance, of the sheer quantity of iron that happens to be dissolved in the ocean at this particular moment in Earth's history. If the iron were less abundant, oxygen might accumulate more quickly. If the iron were more abundant, the delay might stretch even longer. But the iron is what it is, and so the timeline unfolds at the pace chemistry allows. Beneath the formin-banded iron formations, beneath the layers of rust settling onto the seafloor, the deeper ocean remains anoxic. The oxygen produced in the shallows never penetrates to the abyss. The deep water holds its dissolved iron, its reduced chemistry, its populations of anaerobic microbes that have never encountered oxygen and would die if they did. The ocean is stratified not just by temperature but by chemistry, with an oxygenated surface layer, thin, ephemeral, dependent on photosynthesis, overlying a vast anoxic interior. This stratification will persist for a very long time, even after oxygen begins to accumulate in the atmosphere, even after the surface ocean becomes fully oxygenated. The deep ocean will be the last refuge of Archean chemistry, the last place where iron drifts freely and life remains strictly anaerobic. The iron, then, is not just a reactant but a timekeeper. Its abundance sets the pace of planetary change. As long as iron remains in solution, the transformation cannot complete. The atmosphere cannot gain oxygen. The planet cannot transition to the chemistry that will define the next 2 billion years. The iron must be exhausted first, precipitated out, buried in sediments that will eventually become the banded iron formations mined today for steel and industry. Only when the ocean is depleted of dissolved iron, only when the buffer is consumed, can oxygen begin to rise. And so, the iron waits, drifting in the dark water, unreactive and patient, while above it the cyanobacteria multiply, and the first oxygen molecules rise like bubbles toward a sky that is not yet ready to receive them. Somewhere in the shallows, a mutation occurs. It is not dramatic, not sudden in any meaningful sense. A gene duplicates, perhaps, or a regulatory sequence shifts, allowing an enzyme to catalyze a reaction it could not catalyze before. The organism that carries this mutation is a cyanobacterium, a single-celled photosynthetic microbe living in a stromatolite mat or drifting in the sunlit surface water. The mutation allows it to split water molecules, H2O, and extract electrons from them, rather than relying on hydrogen sulfide or ferrous ion or organic molecules as electron donors. This is oxygenic photosynthesis, and it is an accident. The organism does not benefit from the oxygen it produces. Oxygen is toxic to most of the biochemistry that has evolved in the Archean Ocean. It reacts with iron-sulfur clusters in proteins, damages cell membranes, disrupts metabolic pathways that depend on a reducing environment. The cyanobacterium that first evolves oxygenic photosynthesis must also evolve defenses against the oxygen it creates, enzymes to neutralize reactive oxygen species, mechanisms to export the oxygen out of the cell before it causes harm. The oxygen is waste, a dangerous byproduct, tolerated only because the ability to use water as an electron source is so advantageous. And it is advantageous. Water is everywhere. It is the most abundant molecule on the planet's surface, present in every environment where life exists, unlimited and free. Other electron donors, hydrogen sulfide, ferrous iron, organic compounds are locally abundant but globally scarce, concentrated near hydrothermal vents or in specific niches where the chemistry permits them. Water, by contrast, is universal. A photosynthetic organism that can use water as its electron source can live anywhere light penetrates, can colonize any shallow sea, any tidal pool, any sunlit surface. The advantage is overwhelming, and so the mutation spreads, not quickly. Evolution operates on geological timescales in this era, measured in millions of years rather than generations. The first cyanobacteria to evolve oxygenic photosynthesis are rare, perhaps confined to a single population in a single bay. They compete with other photosynthesizers that still rely on hydrogen sulfide, with heterotrophs that consume organic matter, with methanogens and sulfate reducers and all the other microbes that have colonized the ocean. The oxygen they produce reacts with the environment immediately, with dissolved iron, with reduced minerals, with organic molecules, and never accumulates. For a long time, perhaps tens or hundreds of millions of years, oxygenic photosynthesis remains a minor metabolic pathway, a niche adaptation, one strategy among many. But the cyanobacteria are persistent. They build stromatolites, layered structures of sediment and microbial mat that grow slowly upward, centimetre by centimetre over thousands of years. The stromatolites trap sediment, bind it with sticky extracellular polymers, create a stable substrate for more growth. They form in shallow water, where light is abundant and wave action is gentle enough not to destroy them. The structures become habitats, microenvironments where different microbes colonize different layers, cyanobacteria at the top, where light penetrates, sulfate reduces below, where oxygen cannot reach, a gradient of chemistry and ecology compressed into a few centimetres of vertical space. The stromatolites survive, they fossilize, and when geologists find them billions of years later, they recognize the structures as evidence of early life, as some of the oldest biosignatures preserved in rock. The stromatolites in the Archean are not fundamentally different from stromatolites that form today in places like Shark Bay. Australia, where conditions approximate the ancient past, the same basic process, microbial mat growth, sediment trapping, slow upward accretion, operates across billions of years, a continuity of form that transcends almost unimaginable spans of time. The oxygen produced by these early cyanobacteria does not escape into the atmosphere. It reacts with the dissolved iron in the ocean, precipitating iron oxides that settle to the seafloor. It reacts with reduced gases, methane, hydrogen sulfide, oxidizing them before they can reach the air. It reacts with organic matter, with minerals, with anything in the environment that can be oxidized. The ocean and the crust act as enormous sinks, absorbing the oxygen as fast as it is produced, preventing any accumulation. This phase, sometimes called the pre-great oxidation event or the long fuse before the explosion, lasts for hundreds of millions of years. During this time, the cyanobacteria spread. They colonize new habitats, diversify into new species, refine their biochemistry. They form vast mats in shallow seas, covering square kilometers of seafloor with layered microbial communities. They drift in the open ocean, forming planktonic populations that photosynthesize in the surface water and die. Sinking as organic particles that feed deeper ecosystems, they outcompete other photosynthesizers, not through any inherent superiority but through sheer persistence, through the advantage of using an unlimited electron source. Slowly, incrementally, the oxygen flux increases, but still the oxygen does not accumulate. The sinks are too large, too reactive. The dissolved iron in the ocean is measured in gigatons, a reservoir so vast it could consume the output of photosynthesis for millions of years without being depleted. The reduced minerals on land, sulfides, ferrous silicates, are equally abundant, equally ready to react with any oxygen that reaches them. And so the oxygen is consumed, locked away in rust and oxidized rock, buried in sediments, hidden from the atmosphere. The planet remains in its Archean state, reducing and anoxic, despite the growing population of oxygen-producing microbes. There is a certain irony to this. The organisms that will eventually transform the planet are already present, already producing the molecule that will change everything. But the transformation cannot proceed until the environment is ready to receive it. The oxygen is not the limiting factor. The cyanobacteria are not the limiting factor. The limiting factor is the iron, the methane, the reduced minerals, all the chemistry that has accumulated over billions of years, all the sinks that must be filled before oxygen can overflow into the atmosphere. The accident has already happened. The evolutionary innovation is complete, but the planetary consequences are delayed, held in suspension, waiting for the buffering capacity of the ocean to be exhausted. And so the cyanobacteria continue their work, splitting water in the sunlight, releasing oxygen into the water, while the iron continues to precipitate and the banded iron formations continue to grow. The process is unwitnessed, unremarked, invisible. There is no sound, no colour shift, no marker that anything has changed. The ocean looks the same as it did 100 million years earlier. The sky remains the same hazy orange or grey. The land is still sterile, but the chemistry is shifting, molecule by molecule, and the clock is ticking down toward a threshold that, once crossed, cannot be reversed. The mutation that enables oxygenic photosynthesis is not rare in evolutionary terms. Similar pathways evolve independently in different lineages, or are transferred horizontally through gene exchange, spreading the capability across the microbial world. But the specific combination, the ability to split water, the defenses against oxygen toxicity, the ecological success, comes together in the cyanobacteria, and they become the dominant architects of the transformation. They're not trying to change the world. They're simply living, metabolizing, reproducing, following the logic of chemistry and natural selection. The planetary transformation is a side effect, unintended and unstoppable. The accident has happened, the oxygen is being made, and the Earth, patient and slow, begins its long, involuntary reorganization. The rust begins to fall. It falls slowly, particle by particle, drifting through the water column in a descent that takes days or weeks, depending on the size of the grain and the density of the surrounding water. Each particle is microscopic, a flake of iron oxide no larger than a bacterium. Formed when dissolved, ferrous iron encounters oxygen and oxidizes instantly into its ferric state. The ferric iron is insoluble. It cannot remain dissolved, and so it precipitates, aggregates with other particles, and begins the long drift downward toward the seafloor. The particles are red when they form, or rust brown, depending on the exact mineralogy: hematite, magnetite, goethite, minerals whose names will be given much later by scientists studying rocks that were once seafloor. The colour comes from the way iron oxides absorb and reflect light, the same chemistry that makes rust red on a nail left in the rain. The same process now occurring on a planetary scale. The ocean, in the zones where cyanobacteria are producing oxygen, takes on a faint reddish tint in the water column, a haze of falling rust that never quite settles, constantly replenish from above as more oxygen is produced and more iron oxidizes. The particles settle onto the seafloor in layers. Each layer is thin, perhaps a few millimeters thick, the accumulation of years or decades of steady precipitation. The layers compact under their own weight, lose water, begin the slow process of lithification that will eventually turn them into rock. Between the layers of iron oxide, other sediments accumulate, fine clay, silica precipitated from seawater, organic matter from dead microbes. These form the dark bands, the black or grey stripes that alternate with the red iron layers. The result is a banded structure, visible to the eye, rhythmic and repetitive, a record written in rust. The banded iron formations, BIFs, are forming now, in this moment, across the floors of Archean oceans. They form in shallow seas and deep basins, in tropical latitudes and near the poles. Wherever cyanobacteria are producing oxygen and dissolved iron is available to react with it. The formations are not continuous. They form in pulses, in episodes, in cycles that might correspond to seasonal changes in photosynthesis, or longer-term fluctuations in ocean chemistry, or variations in the supply of iron from hydrothermal vents. The bands record all of this, each stripe a data point, each transition a shift in conditions. Some of the banded iron formations are enormous. They extend for hundreds of kilometers, cover areas the size of modern countries, contain billions of tons of iron locked into rock. These deposits will one day be mined for steel, excavated in vast open pits, their layered structure exposed in cliffs that show the banding clearly, red, black, in alternations so regular it almost looks artificial. But there is nothing artificial about it. The bands form according to chemistry, according to the availability of reactants and the rate of precipitation, according to processes that are entirely natural and entirely slow. The formation of the BIFs consumes oxygen. Every molecule of oxygen produced by cyanobacteria reacts with iron before it can do anything else. The oxygen never reaches the atmosphere, never accumulates in the water column beyond the immediate vicinity of the microbial mats. It is consumed as fast as it is made, locked into minerals, buried as rust. This means the planet is producing oxygen, has been producing it for millions of years, but shows no sign of it in the atmosphere. The oxygen is hidden, stored in rock, the evidence visible only in the banded iron formations themselves. This process is often described as a delay, a buffering period. A time when oxygen production ramps up but atmospheric oxygen remains zero. The description is accurate but undersells the scale. The buffering period lasts for hundreds of millions of years. The amount of iron that must be oxidized before the ocean is depleted is staggering. Estimates suggest that the dissolved iron in the Archean Ocean could consume the equivalent of all the oxygen in the modern atmosphere many times over. The banded iron formations represent this consumption, this vast chemical sink, each layer a tiny fraction of the total, each formation a chapter in the long story of oxygen's arrival. The rust accumulates on the seafloor in specific places. It does not form everywhere, only in basins where the conditions are right, shallow enough for photosynthesis, deep enough for sediment to accumulate undisturbed, stable enough for the iron to precipitate without being eroded away by currents. The largest banded iron formations form on continental shelves, along the margins of the small proto-continents that exist in this era. They form in rifts and subsiding basins, in places where the crust is actively spreading or sinking, creating space for thick sequences of sediment to pile up. Over time, these sediments become rock, are buried under more sediments, are heated and compressed by the weight above them, undergo diagenesis and low-grade metamorphism. The chemistry of the banding is not fully understood. Some bands are rich in hematite, others in magnetite, others in siderite or other iron-bearing minerals. The differences suggest variations in oxygen concentration, in pH, in the presence of other dissolved species that affect which minerals precipitate. Some bands contain organic carbon, suggesting that microbial activity played a role in their formation. Other bands are purely inorganic, formed by purely chemical processes. The formations are heterogeneous, complex, full of details that hint at environmental conditions but do not spell them out clearly. Scientists studying the banded iron formations look for patterns, periodicities in the banding that might correspond to astronomical cycles, changes in mineralogy that might indicate shifts in ocean chemistry, trace element signatures that might reveal the temperature or salinity of the ancient seawater. They find some patterns, lose others, argue over interpretations. The formations are a rich source of data, but the data is incomplete, transformed by time and heat and pressure, only partially preserved. Still, the bands themselves are unambiguous. Iron was dissolved in the ocean, oxygen was produced, the two reacted, the rust fell. The story is written in stripes. In some places, the banded iron formations are interbedded with volcanic rocks, basalts and tuffs that erupted onto the seafloor during the same period when the iron was precipitating. This allows the formations to be dated, at least approximately, using radiometric methods. The dates cluster around certain ages, 2.5 billion years ago, 1.9 billion years ago, with smaller formations scattered throughout. The clustering suggests that banded iron formation was not a continuous process, but an episodic one, concentrated in specific time intervals when the ocean chemistry was just right. Between these intervals, iron may have continued to dissolve into the ocean, building up the reservoir that would precipitate in the next pulse. The falling rust is silent. There is no sound to the precipitation, no noise as the particles drift downward, no splash as they settle onto the mud. The process is as quiet as snow falling on a windless day, as imperceptible as the slow accretion of dust. And yet the scale is planetary. Across millions of square kilometres of seafloor, the rust is falling, day after day, year after year, century after century. The cumulative effect is enormous. Enough iron oxide to build mountains, to fill basins, to create rock formations that will endure for billions of years and eventually supply the raw material for human industry. The cyanobacteria, drifting in the sunlit water above, do not witness the rust they create. They produce oxygen. The oxygen reacts, and the iron falls away into the depths, out of sight, accumulating in layers on a seafloor they will never see. The cycle continues. The bands grow, and the dissolved iron in the ocean, vast as it is, begins very slowly to diminish. The poison accumulates slowly, for hundreds of millions of years. The oxygen produced by cyanobacteria has been consumed immediately, locked into rust, buried in banded iron formations, prevented from reaching the atmosphere. But the sinks are not infinite. The dissolved iron in the ocean, enormous as the reservoir is, gradually depletes. The reduced minerals on the seafloor, the sulfides and ferrosilicates, oxidize and are buried under fresh sediment, and as the sinks diminish, the oxygen has nowhere else to go. It begins to accumulate in the water column, then diffuses across the ocean atmosphere boundary, leaking into the air molecule by molecule. The transition is not abrupt. There is no single moment when the atmosphere gains oxygen, no threshold crossed in a day or a year. Instead, the process unfolds over tens of millions of years, possibly longer, a gradual shift in atmospheric chemistry that happens too slowly to be perceived by anything alive at the time. The oxygen concentration rises from 0 to trace amounts, parts per million, then parts per thousand, while the atmosphere remains dominated by nitrogen, carbon dioxide, and methane. The change is invisible, unremarkable, written only in the chemistry of rocks that will preserve the transition. This is the Great Oxidation Event, the GOE, though the name suggests a drama that the process itself does not possess. It is great in scale, certainly, planetary in scope, irreversible in its consequences, but it is not sudden, not catastrophic in the sense of happening all at once. It is a slow leak, a creeping transformation, chemistry changing faster than geology but slower than biology, operating on timescales that fall awkwardly between the two. The oxygen rises. The methane, which has kept the planet warm for so long, begins to react with the oxygen and is destroyed. Methane and oxygen cannot coexist in an atmosphere for long. The two molecules react readily, combining to form carbon dioxide and water vapour. The reaction releases energy, and in an oxygen-rich atmosphere it would be rapid, even explosive. But the early Proterozoic atmosphere is not oxygen-rich. The oxygen concentration is still low, measured in single-digit percentages at most, and the methane concentration is falling but not yet eliminated. The two gases coexist uneasily, reacting slowly, generating a haze of organic molecules that hang in the atmosphere and scatter sunlight. The sky, already hazy, becomes hazier. The colour shifts, perhaps, from orange to grey, or from one shade of grey to another. The exact hue is unknowable, a detail lost in the transformation. The loss of methane has consequences. Methane is a powerful greenhouse gas, far more effective at trapping heat than carbon dioxide. Its presence in the Archean atmosphere helped compensate for a sun that burned dimmer than it does now, keeping the surface warm enough for liquid water despite the lower stellar output. As the methane is destroyed by oxygen, the greenhouse effect weakens, the planet begins to cool, the tropics remain warm, but the higher latitudes chill, ice begins to form, first at the poles, then spreading toward the equator in glaciers that carve valleys and deposit moraines as they advance. This cooling will eventually lead to the Huronian glaciation, one of the first snowball Earth events, where ice sheets advance to near equatorial latitudes and the planet enters a deep freeze. But that glaciation is still in the future, millions of years away. For now, the cooling is gradual, the ice limited, the oceans still mostly ice-free. The oxygen continues to rise, the methane continues to fall, and the planet's climate adjusts slowly to its new chemistry. The oxygen that accumulates in the atmosphere is toxic to most of the life that has evolved in the Archean. Anaerobic organisms, those that thrive in the absence of oxygen, that metabolize without it, that are poisoned by its presence, suddenly find their habitats shrinking. The surface ocean, once a safe environment, becomes hostile as oxygen diffuses downward from the atmosphere. The shallow sediments, once anoxic and rich in reduced compounds, oxidize and lose the chemistry that supported sulfate reducers, methanogens, and other anaerobes. These organisms retreat to the deep ocean, to anoxic basins, to sediments where oxygen cannot penetrate. Refuges that will remain habitable for billions of years, but are far smaller than the global ocean they once dominated. For the anaerobes, the great oxidation event is an extinction, or at least a mass contraction. Whole lineages disappear from the surface environment, confined to niche habitats or eliminated entirely. The microbial ecosystems that flourished in the Archean are restructured, simplified, their diversity reduced by the new chemistry. The losses are invisible, leaving no fossils, no clear record in the rock. But the genetic evidence, preserved in the genomes of modern microbes, suggests that the great oxidation event was a bottleneck, a pruning, a moment when much of life's diversity was lost or pushed into the margins. For the cyanobacteria, the event is a triumph, though they do not experience it as such. They've evolved defences against oxygen, enzymes that neutralize reactive oxygen species, mechanisms to manage the poison they produce. To them, oxygen is a waste product, an inconvenience, but not a threat. And as the oxygen concentration rises, organisms that cannot tolerate it die back, leaving more space for the cyanobacteria to expand. They colonize new habitats, form thicker mats, build larger stromatolites. Their success is accidental, a byproduct of a defensive adaptation, but it reshapes the biosphere nonetheless. Other organisms begin to evolve oxygen tolerance. Some develop enzymes similar to those in cyanobacteria. borrowing the biochemistry through horizontal gene transfer or evolving it independently. Others learn to avoid oxygen, to seek out microenvironments where it is absent or present only in low concentrations. Still others, a few, a very few, begin to experiment with using oxygen as an energy source, metabolizing it instead of fearing it, discovering that the same reactivity that makes oxygen toxic also makes it a potent oxidant for harvesting energy. This is the beginning of aerobic respiration, though it will take millions of years to refine and spread. The atmosphere itself becomes a new kind of environment. Before the GOE, the atmosphere was simply there, a passive backdrop, a reservoir of gases that organisms largely ignored. After the GOE, the atmosphere becomes reactive, chemically active, capable of transforming surfaces and influencing biology. Oxygen reacts with methane, with hydrogen sulfide, with ammonia, destroying these reduced gases and replacing them with oxidized products, carbon dioxide, sulfur dioxide, nitrogen. The atmospheric composition shifts toward the mixture that will define the next 2 billion years, a composition still far from modern but fundamentally different from the Archean. The rocks on land begin to change. Oxygen in the atmosphere reacts with minerals at the surface, oxidizing iron in soils and riverbeds, turning grey stone red. The first red beds appear in the geological record, sediments deposited on land or in shallow water, stained with iron oxide. Evidence that oxygen has reached concentrations high enough to affect surface chemistry. These red beds are markers, indicators of atmospheric oxygen, and their appearance in the stratigraphic column is one of the clearest signs that the great oxidation event is underway. The transition is not smooth. The oxygen concentration does not rise steadily but fluctuates, spiking and crashing over millions of years as the sources and sinks of oxygen vary. At times, oxygen production outpaces consumption, and the concentration rises rapidly. At other times, new sinks open up, fresh volcanic rock is exposed, reduced minerals weather out of continental interiors, and the oxygen is consumed again. The concentration falling, the atmosphere oscillates, unstable, searching for a new equilibrium. And through all of this, the cyanobacteria continue their work, splitting water in the sunlight, releasing oxygen into a world that is slowly learning to tolerate it. They are not trying to transform the planet, they are simply metabolizing, following the logic of their biochemistry, surviving. But the oxygen they produce is irreversible. Once released, it reacts, it spreads, it changes everything it touches. The poison has become air, high above the surface to stir. In the thin upper reaches of the atmosphere, oxygen molecules drift into a region where ultraviolet light is intense and unfiltered. The UV radiation streaming from the sun strikes the oxygen molecules, O2, and splits them apart into individual oxygen atoms. The atoms are reactive, unstable, searching for something to bond with. Most of them recombine into O2 almost immediately, reforming the molecules they came from. But some encounter other oxygen molecules first, colliding in three-body reactions that require the presence of a third molecule to carry away excess energy. When this happens, the atoms bond to the O2 molecules, forming O3, ozone. The ozone is a trace gas, present in concentrations measured in parts per million even at its densest. It forms a layer. Though layer is perhaps too strong a word, it is more a region, a zone of elevated concentration between 15 and 35 kilometers above the surface. Depending on latitude and atmospheric conditions, the ozone itself is pale blue, though the concentration is too low to give the sky any noticeable tint. It is invisible from the ground, undetectable without instruments. A molecule that exists in quantities so small it would be negligible except for one critical property. It absorbs ultraviolet radiation. UV radiation comes in three bands defined by wavelength: UVA, UVB, and UVC. The shortest wavelengths, UVC, are the most energetic and the most damaging to organic molecules. They break apart DNA, destroy proteins, kill cells with efficiency in the Archean atmosphere. Before oxygen and before ozone, UVC radiation reached the surface unimpeded, flooding the land and the upper layers of the ocean with sterilizing light. Life survived only in the depths, or beneath microbial mats thick enough to absorb the radiation, or in other sheltered environments where UV could not penetrate. Now, with ozone forming in the stratosphere, the UVC is absorbed before it reaches the surface. The ozone molecules intercept the UV photons, absorb their energy, and are split apart in the process. The oxygen atoms released by this splitting recombine into ozone again, or into O2, and the cycle continues, ozone forming, breaking apart, reforming, in a steady-state equilibrium that depends on the supply of oxygen from below and the flux of UV radiation from above. The process is called the Chapman cycle, though the scientist who described it will not be born for another 2 billion years. The chemistry operates regardless, indifferent to names or understanding. The formation of the ozone layer is a consequence of the Great Oxidation Event, not a cause. The oxygen must accumulate in the atmosphere first, reaching concentrations high enough that some of it diffuses into the stratosphere where UV light is strong. The exact threshold is debated, perhaps 1% of modern oxygen levels, perhaps less, but once that threshold is crossed, ozone begins to form and the UV flux at the surface begins to drop. The transition is gradual, spread over millions of years. As the oxygen concentration rises and the ozone layer thickens and the amount of UV radiation reaching the ground steadily declines. The effect on life is profound, though the life in question is still entirely microbial and the effect will not be fully realized for hundreds of millions of years. With UVC blocked, the land surface becomes habitable, or at least less lethal. Organisms that once could survive only underwater or in deep shade can now tolerate exposure to sunlight, at least for brief periods. The upper layers of the ocean, previously scoured by UV, become gentler environments. The chemistry of the surface changes, too, as UV-driven reactions slow and oxygen-driven reactions take over. The atmosphere, once a source of hazard, becomes a shield. But the shield is not perfect. UVB radiation still reaches the surface, though in reduced amounts. UVB is less energetic than UVC, less immediately lethal, but still damaging over time. It still causes DNA mutations, still disrupts cellular processes, still selects for organisms with repair mechanisms or protective pigments or other defenses. Life adapting to the surface will need to evolve these defenses, will need to tolerate UVB even as UVC is blocked. The ozone layer is helpful, necessary even, but it is not sufficient. Biology must do the rest. The ozone layer also affects climate. Ozone absorbs not just UV radiation but also infrared, trapping heat in the stratosphere and influencing the temperature structure of the atmosphere. The stratosphere becomes warmer than it would otherwise be, creating a temperature inversion that stabilizes the atmosphere and reduces vertical mixing. This has consequences for weather, for atmospheric circulation, for the distribution of gases and aerosols. The ozone layer, small as it is, alters the physics of the entire atmosphere, creating a structure that will persist for billions of years. The concentration of ozone varies with latitude, with season, with atmospheric dynamics. It is thickest near the poles, where cold temperatures and stratospheric circulation concentrate the ozone molecules. It is thinner near the equator, where warmer temperatures and faster chemical reactions deplete it more quickly. The variation creates patterns, gradients, regions where UV protection is stronger or weaker. These patterns will matter later, when life begins to colonize the land, when organisms must adapt to different UV intensities at different latitudes. For now, the patterns are simply there, invisible and unremarked, a detail of atmospheric chemistry. The formation of ozone is not instantaneous. It takes time for oxygen to diffuse into the stratosphere, time for the Chapman cycle to establish itself. Time for the ozone concentration to build to levels that effectively block UVC. During the transition, the UV flux at the surface fluctuates, following the oxygen concentration as it rises and falls. There are periods when the ozone layer is thin, when UV protection is weak, when the surface is nearly as hostile as it was before. There are other periods when the ozone thickens, when UV drops, when conditions improve. The transition is not linear, not smooth, but jagged and irregular, tracking the instability of the oxygen concentration itself. Scientists studying the ozone layer, the modern ozone layer, the one that exists today, have learned to read its chemistry, to measure its thickness, to detect changes caused by human activity or natural variation. They understand the Chapman cycle, the role of chlorine and bromine in depleting ozone, the ways in which CFCs and other industrial gases threaten the layer. But the ancient ozone layer, the one forming for the first time in the early Proterozoic, leaves no direct evidence. There are no measurements, no preserved samples of stratospheric air. The only evidence is indirect, the presence of red beds indicating surface oxidation, the isotopes of sulfur that change when UV filtering begins, the eventual colonization of a land by life that could not have survived without UV protection. The ozone layer is a shield formed from poison. The oxygen that creates it is toxic to most Archean life, the product of a metabolism that disrupts the reducing chemistry of the ancient world. But the ozone itself, formed in the high atmosphere where nothing lives, becomes one of the conditions that will eventually allow life to leave the ocean, to spread across the land, to diversify into the biosphere that will dominate the planet for the next 2 billion years. The shield is an accident, a side effect, a consequence of chemistry operating according to its own rules. It is not designed, not intended, but it is essential, and so the ozone form, molecule by molecule, in the thin air above a planet that is slowly, inexorably, learning to tolerate oxygen. The ice begins in the high latitudes, creeping outward from the poles in sheets that thicken and spread with each passing century. The formation is slow at first, almost tentative. Seasonal snowfall that does not fully melt in summer, accumulating year after year until the weight compresses the lower layers into ice. The ice reflects sunlight, bouncing radiation back into space, cooling the surface further. More ice forms. The boundary between frozen and unfrozen terrain advances toward the equator, carving through landscapes that have never known cold, burying coastlines under kilometers of frozen water. This is the Huronian glaciation, one of the earliest snowball Earth events in the geological record, occurring roughly 2.4 to 2.1 billion years ago. The name comes from the rocks that preserve evidence of the glaciation, tillets and glacial deposits found along the northern shore of Lake Huron, studied and mapped by geologists who recognized the signature of ancient ice. The glaciation lasts for hundreds of millions of years, waxing and waning in intensity, with ice advancing and retreating in cycles that may correspond to orbital variations or changes in volcanic activity or fluctuations in atmospheric chemistry. The cause is tied to the Great Oxidation Event, to the loss of methane from the atmosphere. Methane has kept the planet warm for most of the Archean, compensating for a sun that burns 30% dimmer than it will in the future, as oxygen rises and reacts with methane. The greenhouse effect weakens. Carbon dioxide remains in the atmosphere, but carbon dioxide alone is not enough to maintain the same warmth. The planet cools. The poles freeze first, then the ice creeps southward, following the logic of albedo and thermodynamics, self-reinforcing as more reflective ice replaces darker ocean or land. The glaciers reach low latitudes, possibly extending to within 10 or 15 degrees of the equator. Evidence for this comes from glacial deposits found in rocks that, when their position is reconstructed using paleomagnetism, were located near tropical latitudes when the deposits formed. The ice does not cover the entire planet, There is debate about whether this qualifies as a true snowball Earth or merely a severe glaciation, but it comes close. Much of the ocean surface freezes over. The ice sheets on land grow thick enough to flow under their own weight, grinding bedrock into fine powder, transporting boulders hundreds of kilometers from their source. Life persists. It must, because life exists after the glaciation and shows continuity with life before. The microbes that have colonized the ocean do not go extinct. They survive, perhaps in pockets of open water near the equator, or beneath the ice where liquid water remains in contact with the seafloor, or in hydrothermal systems where heat from the Earth's interior keeps conditions habitable. The cyanobacteria, architects of the oxygen that triggered the cooling, continue to photosynthesize wherever light penetrates the ice. Their populations contract, their productivity drops, but they do not disappear. The ice is not uniform. It varies in thickness, in clarity, in the amount of debris frozen within it. Near the coasts, where glaciers carve into the ocean, the ice is thick and opaque, filled with rock flour and entrained boulders. Farther from shore, the sea ice is thinner, possibly only a few meters deep, thin enough in places for sunlight to penetrate and support photosynthesis in the water below. The ocean beneath the ice remains liquid in most places, kept from freezing completely by geothermal heat and by the salinity of the water, which lowers its freezing point. The ice advances in pulses, not steadily. There are periods when the glaciers grow rapidly, surging forward, driven by changes in snowfall or temperature or the dynamics of ice flow. There are other periods when the ice stalls or retreats slightly, melting at the margins faster than it accumulates in the interior. The cycles are recorded in the sediments, layers of glacial till interbedded with layers of fine sediment deposited during warmer intervals, evidence that the climate oscillated rather than remaining locked in a single frozen state. The atmosphere during the glaciation is different from before or after. The oxygen concentration is still relatively low, perhaps 1 to 10% of modern levels, but rising. The carbon dioxide concentration is also low, drawn down by weathering and possibly by reduced volcanic outgassing. The methane is nearly gone, oxidized away by the rising oxygen. The atmospheric pressure may be lower than in the Archean, or it may be roughly the same. The evidence is ambiguous. What is clear is that the greenhouse effect is weak. The planet's energy balance is tilted toward cooling, and the ice continues to spread. The glaciers carve the land, they gouge valleys, strip away soil, polish bedrock into smooth curves marked with striations, parallel scratches left by rocks embedded in the ice as it flows. These striations are visible today in rocks 2 billion years old, preserved through metamorphism and tectonic rearrangement, pointing in directions that indicate the flow of ice sheets long vanished. The glaciers also deposit debris, unsorted mixtures of clay, sand, gravel, and boulders dropped wherever the ice melts, forming tillites that harden into rock and preserve the record of glaciation. Some of the glacial deposits contain drop stones, isolated boulders or cobbles embedded in fine-grained sediment, out of place and puzzling until their origin is understood. The drop stones are carried by icebergs, frozen into the ice as glaciers carve into the ocean, then released when the icebergs melt, sinking through the water column and landing on the seafloor far from their source. The presence of drop stones in sediments that otherwise show no sign of glaciation is evidence of ice-covered seas, of icebergs drifting across an ocean that was cold but not entirely frozen. The duration of the Huronian glaciation is staggering. Hundreds of millions of years, long enough for mountain ranges to erode, for new volcanic provinces to form, for entire tectonic cycles to complete. The ice is not constant during this time. It advances and retreats, thickens and thins, responding to forcings that are only partially understood. But the overall state is cold, colder than the planet has been before. colder than it will be again until the next snowball Earth event hundreds of millions of years in the future. The end of the glaciation comes gradually, as the beginning did. Volcanic activity continues throughout the glaciation, releasing carbon dioxide into the atmosphere. The ice, being highly reflective, prevents much of this carbon dioxide from being drawn down by weathering, because weathering requires liquid water and exposed rock, both of which are scarce when the surface is frozen. The carbon dioxide accumulates, slowly rebuilding the greenhouse effect, until eventually the warming overcomes the cooling and the ice begins to melt. The process takes millions of years, the opposite of the advance. A slow thaw that starts at the equator and works its way poleward. As the ice retreats, the ocean warms, photosynthesis resumes at higher rates. Oxygen production increases again. The microbial mats that survive the cold begin to spread, recolonizing habitats that were frozen or inhospitable. The planet enters a new phase, warmer and more stable, though the oxygen concentration is still far below modern levels and the atmosphere is still in transition. The glaciation is over, but its effects linger in the distribution of life, in the chemistry of the ocean, in the sediments that record the advance and retreat of ice. The glaciers leave their mark. The land they carved will never look the same. The life they challenged will evolve new strategies, new tolerances, new biochemistries adapted to a world that can freeze and thaw. And the ice itself, though melted, remains in memory, written in rock, visible to anyone who knows how to read the record. A reminder that planets do not transition smoothly and climate does not change gently. The ice creeps back toward the poles, the world warms, and the oxygen continues to rise. The thaw begins with methane. It seeps from the seafloor, from sediments where organic matter decays in anoxic conditions, from hydrothermal systems where geological processes generate reduced gases. The methane rises through the water column, bubbles through any cracks in the sea ice, escapes into the atmosphere. It is a greenhouse gas, potent and effective, capable of trapping heat far more efficiently than carbon dioxide. As the methane accumulates, the atmosphere warms, the ice at the edges of the glaciers begins to melt, the albedo decreases, more sunlight is absorbed by the darker ocean and land, the warming accelerates. The source of the methane is uncertain, debated among scientists who study this period. Some of it is likely biological, produced by methanogenic archaea that thrive in anoxic sediments, metabolizing simple organic compounds and releasing methane as waste. These organisms have existed since the Archean, flourishing in environments where oxygen is absent and organic matter is available. During the glaciation, their activity may have continued beneath the ice, in sediments where the cold slowed but did not stop their metabolism. The methane they produced would have accumulated in the sediments, trapped by the ice above, building pressure until it began to leak into the water and then the atmosphere. Other methane may be geological in origin, generated by serpentinization, a process where water reacts with ultramafic rocks in the oceanic crust, producing hydrogen that can then react with carbon dioxide to form methane. Serpentinization occurs at hydrothermal systems, at mid-ocean ridges, in any setting where hot rock and water interact. The process is abiotic, independent of life, capable of generating methane in quantities that might be significant on a planetary scale. During the glaciation, serpentinization would have continued, unaffected by the ice, adding methane to the ocean and atmosphere steadily over millions of years. There is also the possibility of methane clathrates, ice-like structures where methane molecules are trapped in cages of water molecules, stable only at low temperatures and high pressures. Clathrates form in cold ocean sediments, accumulating over time as methane from microbial or geological sources is buried and frozen in place. If the ocean warms even slightly, or if pressure decreases due to sea level changes, the clathrates destabilize and release their methane in a sudden pulse. This process, called clathrate destabilization, is a feedback mechanism. Warming releases methane. Methane causes more warming, which releases more methane. The feedback can be abrupt, pushing the climate rapidly from frozen to warm. Whether the methane that ended the Huronian glaciation came from microbes, from serpentinization, from clathrate destabilization, or from some combination of all three is unknown. The evidence is sparse, limited to isotopes in rocks that might indicate a biological or geological source, to models that attempt to reconstruct atmospheric chemistry, to comparisons with later snowball Earth events where methane may have played a similar role. What is clear is that methane increased, the atmosphere warmed, and the ice retreated. The exact mechanism is less certain, lost in the ambiguity of deep time. The warming is not immediate. It takes millions of years for the methane to accumulate to concentrations sufficient to overcome the cooling effect of the ice. During this time, the glaciation persists. The ice remains thick, and the planet stays cold. Volcanic activity continues, releasing carbon dioxide as well as methane, contributing to the slow rebuilding of the greenhouse effect. The carbon dioxide alone might eventually be enough to end the glaciation, but methane accelerates the process, providing a boost that allows the warming to begin sooner and proceed faster than it would with carbon dioxide alone. As the ice melts, the meltwater flows into the ocean, raising sea level, flooding coastal areas that were exposed during the glaciation. The influx of fresh water changes the salinity of the surface ocean, affecting circulation patterns, altering the distribution of nutrients and dissolved gases. The ocean begins to mix more vigorously, driven by temperature differences between the warming surface and the still cold deep layers. Upwelling brings nutrients from the depths to the surface, stimulating photosynthesis, increasing biological productivity. The cyanobacteria, dormant or reduced during the glaciation, begin to proliferate again. The increase in photosynthesis produces more oxygen. The oxygen reacts with the methane in the atmosphere, destroying it, converting it back to carbon dioxide and water vapor. This is a negative feedback. The warming caused by methane triggers processes that remove the methane, stabilizing the climate and preventing runaway warming. The methane concentration peaks, then declines, and the greenhouse effect weakens again. Though not as much as during the glaciation, the climate settles into a new equilibrium, warmer than the glacial state but not as warm as the pre-glaciation Archean. The transition from glaciation to interglacial is recorded in the rock as a shift from glacial sediments, tilites, dropstones, ice-rafted debris, to marine sediments deposited in open water. The boundary between the two is often sharp, a contact that represents the moment when the ice retreated and the ocean advanced. Above the glacial deposits, the rocks are finer grained, better sorted, indicative of deposition in calm water rather than beneath or beside ice. Some of these post-glacial sediments are rich in organic carbon, suggesting that biological productivity surged after the ice melted. As nutrients released from the melting glaciers fertilized the ocean and supported blooms of photosynthetic microbes. There are multiple glacial episodes within the Huronian, multiple advances and retreats of the ice, separated by warmer intervals that might have lasted millions of years. Each episode ends with a thaw, possibly driven by methane, possibly by carbon dioxide, possibly by both. The cycle's not regular, not predictable, but they repeat. Glaciation, thaw, warmth, cooling, glaciation again. The planet oscillates, unable to find a stable state, searching for an equilibrium between the cooling caused by the loss of methane and the warming provided by volcanic carbon dioxide. The methane that ends each glaciation is temporary. It warms the planet, melts the ice, but it does not persist. Oxygen destroys it. Biological processes consume it, and the atmosphere returns to a composition dominated by nitrogen, carbon dioxide, and trace oxygen. The methane spikes, then crashes, leaving behind only isotopic signatures in rocks that hint at its presence. The spikes are brief on geological timescales, lasting perhaps a few million years, but they are sufficient to break the ice, to restart the climate system, to allow warmth to return. The role of methane in Earth's climate will recur throughout geological history. It will warm the planet during other snowball Earth events, will spike during mass extinctions, will fluctuate in response to changes in ocean circulation or biological productivity, or the burial and exposure of organic-rich sediments. Methane is a wild card, a gas whose concentration can change rapidly and whose effects are disproportionate to its abundance. It is a molecule that connects geology, biology, and climate, a bridge between the solid Earth and the atmosphere, a player in feedbacks that can stabilize or destabilize the planetary system. For now, though, the methane does its work quietly, invisibly, seeping from the seafloor and drifting into the air, warming the planet molecule by molecule until the ice begins to melt and the glaciation ends. The process is slow, spread over millions of years, but it is inexorable. The methane accumulates, the temperature rises, the ice retreats, and the planet, locked in cold for hundreds of millions of years, finally begins to thaw. The cells that learn to breathe poison do not choose to. Evolution operates through variation and selection, not intention, and the organisms that first develop aerobic respiration stumble into it the way cyanobacteria stumbled into oxygenic photosynthesis, through mutation, accident, the blind testing of biochemical possibilities. Oxygen is toxic. It damages proteins, disrupts iron-sulfur clusters, generates reactive species that destroy membranes and nucleic acids. But oxygen is also an opportunity. It is a powerful oxidant, capable of extracting more energy from organic molecules than any other metabolic pathway yet evolved. The organisms that can tolerate oxygen, that can harness it, gain an advantage so overwhelming that aerobic respiration will eventually become the dominant metabolism on the planet. The transition is not abrupt. For hundreds of millions of years after oxygen begins to accumulate in the atmosphere, most life remains anaerobic. The deep ocean is still anoxic, the sediments are still reducing, and vast populations of microbes continue to thrive without oxygen, using sulfate or nitrate or fermentation to extract energy from their environment. Aerobic respiration evolves in this context, not as a replacement for anaerobic metabolism, but as a supplement, an additional strategy available in environments where oxygen is present. The first aerobic organisms are likely facultative, capable of switching between aerobic and anaerobic metabolism depending on oxygen availability. The biochemistry of aerobic respiration is complex, requiring a chain of protein complexes embedded in a membrane, each complex transferring electrons from one carrier to the next until the electrons are finally accepted by oxygen, forming water. The process is called the electron transport chain, and it operates like a molecular assembly line, each step carefully controlled, each transfer releasing a small amount of energy that is captured and stored in the form of ATP, adenosine triphosphate, the universal energy currency of life. The efficiency is remarkable. Aerobic respiration extracts roughly 18 times more energy from a glucose molecule than anaerobic fermentation does, a difference large enough to reshape ecosystems. The electron transport chain likely evolves in stages, with components borrowed from earlier metabolic pathways and repurposed for oxygen respiration. Some of the proteins resemble those used in anaerobic respiration, where nitrate or sulfate serves as the electron acceptor instead of oxygen. Other components are unique to aerobic respiration, evolved specifically to handle oxygen's high reactivity and to manage the dangerous intermediates, superoxide, hydrogen peroxide, that form when oxygen is only partially reduced. The pathway is refined over millions of years, optimized through natural selection, until it operates with the precision visible in modern mitochondria. Mitochondria, The organelles that perform aerobic respiration in eukaryotic cells are descended from free-living bacteria that evolved this metabolism. The endosymbiotic event that gave rise to mitochondria occurs much later, perhaps 1 billion years after the Great Oxidation event, but the aerobic bacteria that will eventually become mitochondria are evolving now. In the early Proterozoic, learning to use oxygen as life around them struggles to survive it. The bacteria are small, rod-shaped or spherical, similar in appearance to modern proteobacteria. They live in environments where oxygen is available but not dominant, the surface layers of microbial mats. The interface between oxic and anoxic water, sediments where oxygen penetrates only a few millimeters. The advantage of aerobic respiration is most pronounced in environments where resources are scarce. Anaerobic organisms can thrive in nutrient-rich settings, where organic matter is abundant and competition is limited by factors other than energy. But in nutrient-poor environments, where every molecule of glucose or acetate must be extracted from dilute surroundings, the ability to extract 18 times more energy from each molecule is transformative. Aerobic organisms can survive on lower concentrations of organic matter, can grow faster, can outcompete anaerobes wherever oxygen is present. The advantage compounds over time, and aerobic metabolism spreads. The spread is not linear. Oxygen concentration in the atmosphere fluctuates during the early Proterozoic, rising and falling in response to changes in photosynthetic productivity, volcanic activity, and the weathering of reduced minerals. During periods when oxygen is abundant, aerobic organisms flourish, expanding their range and diversifying into new niches. During periods when oxygen crashes, anaerobes reassert dominance, and aerobic lineages contract or go extinct. The early history of aerobic respiration is punctuated, unstable, marked by expansions and extinctions that track the instability of atmospheric chemistry. The organisms that evolve aerobic respiration also evolve defenses against oxygen toxicity. They produce enzymes, superoxide dismutase, catalase, peroxidase, that neutralize reactive oxygen species before they can cause damage. These enzymes are essential. Without them, the oxygen used in respiration would kill the cell before the energy could be harvested. The defenses are so effective that they're conserved across all aerobic life. Present in bacteria, archaea, and eukaryotes, evidence of their ancient origin and their universal necessity. Some organisms evolve oxygen tolerance without evolving aerobic respiration. They develop the defenses but continue to use anaerobic metabolism, living in environments where oxygen is present but not using it for energy. These organisms occupy a middle ground, neither strictly aerobic nor strictly anaerobic, capable of surviving in the transitional environments that characterize the early Proterozoic ocean. They are facultative anaerobes, opportunists, able to exploit whatever resources are available without committing fully to one metabolic strategy. The evolution of aerobic respiration changes the carbon cycle. Aerobic organisms break down organic matter more completely than anaerobes do, mineralizing it back to carbon dioxide rather than leaving partially oxidized intermediates like methane or acetate. This increases the efficiency of carbon recycling, reduces the accumulation of organic carbon in sediments, and alters the balance between photosynthesis and respiration in the ocean. The changes are subtle at first, but they accumulate over time, shifting the ocean toward a state where organic carbon is turned over more rapidly and buried less readily. The presence of oxygen also enables new biosynthetic pathways. Certain molecules, sterols, for example, which stabilize cell membranes in eukaryotes, can only be synthesized in the presence of oxygen. The enzymes that make sterols require molecular oxygen as a substrate, using it to modify precursor molecules into the complex ring structures that define sterol chemistry. Before oxygen, these molecules could not exist. After oxygen, they become possible, opening new biochemical territory that will eventually be explored by eukaryotes and contribute to their success. The early aerobic organisms are not dominant. They are rare, confined to specific niches, outnumbered by the anaerobes that have occupied the planet for billions of years. But they are persistent, and they are adapted to a world that is becoming more oxygenated. As the oxygen concentration continues to rise, as the ocean surface becomes progressively more oxic, the aerobic organisms spread. They colonize new habitats, diversify into new species, refine their metabolism. They do not replace the anaerobes entirely. Anoxic environments persist. And anaerobic life continues to thrive in the deep ocean, in sediments, in any place oxygen cannot reach. But the balance shifts. Aerobic metabolism becomes more common, more important, more central to the functioning of ecosystems. The poison, through evolution, becomes fuel. The molecule that killed becomes the molecule that powers life. And the cells that learn to breathe it, tentatively at first, will inherit a planet that is slowly, inexorably, being remade by the very gas they have learned to tolerate. The stromatolites continue their work, indifferent to the revolution unfolding around them. They grow in shallow water, in bays and lagoons where wave action is gentle and sedimentation is steady, building upward at rates measured in millimeters per year. The cyanobacteria that form them, the same cyanobacteria that produce the oxygen transforming the planet, live in thin films at the surface of the structures, photosynthesizing during the day, binding sediment with sticky extracellular polymers, creating layers that will harden into rock over time. The structures are domes, mounds, columns, depending on the local conditions, water depth, current strength, sediment supply. Some grow as isolated pillars, rising a meter or more above the surrounding seafloor, sculpted by currents that flow around them. Others form continuous sheets covering square kilometers of shallow seabed in undulating, layered mats. The geometry is determined by the interaction between microbial growth and physical environment, a partnership between biology and hydrodynamics that produces forms recognizable across billions of years. Each layer in a stromatolite represents a growth interval, a period of time when the cyanobacteria at the surface were active, trapping sediment and precipitating minerals. The layers are thin, often less than a millimeter, sometimes much thinner. They alternate between light and dark, between sediment-rich and organic-rich, between layers dominated by mineral precipitation and layers dominated by microbial mat. The alternation may correspond to daily cycles, to seasonal changes, to longer-term fluctuations in growth conditions. The exact rhythm is difficult to determine, lost in the compaction and diagenesis that transform the mat into rock. The stromatolites are ancient. The oldest confirmed examples date to more than 3.5 billion years ago, formed in the Archean when the atmosphere was still anoxic and the ocean was rich with dissolved iron. Those early stromatolites were built by photosynthetic bacteria that did not produce oxygen, that use hydrogen sulfide or ferrous iron as electron sources. But by the time of the Great Oxidation Event, stromatolites are being constructed by cyanobacteria, by oxygen-producing microbes, and the structures become factories of atmospheric transformation, tiny local sources of a gas that will eventually saturate the planet. The microbial communities within stromatolites are layered, stratified by light and chemistry, at the surface, where light is brightest. Cyanobacteria dominate, forming dense mats that photosynthesize and release oxygen. Just below, in a zone where oxygen is present but light is dimmer, aerobic heterotrophs consume organic matter, breaking down dead cells and metabolic waste. Deeper still, where oxygen is absent or nearly so, anaerobic microbes take over, sulfate reducers, methanogens, fermenters, recycling nutrients and producing gases that bubble up through the mat or dissolve into the surrounding water. The stromatolite is a microcosm, a miniature ecosystem compressed into a structure a few centimeters or meters tall. The growth of stromatolites is slow, patient, cumulative. A structure that rises a meter above the seafloor might represent thousands or tens of thousands of years of growth, layer upon layer, each thin film of cyanobacteria contributing a fraction of a millimetre before being buried by sediment and replaced by a new film above. The process is repetitive, monotonous, governed by the daily cycle of photosynthesis and the steady supply of sediment from the surrounding water. There is no acceleration, no climax, just continuous accretion, year after year, until the structure reaches a size where it is stable, where wave action no longer threatens to topple it, where it becomes a permanent feature of the landscape. Stromatolites are rare in the modern ocean, found only in a few locations where conditions exclude the grazing animals that would otherwise consume the microbial mats before they could build structures. Shark Bay in Western Australia is one such location, where hypersaline water keeps grazers away and stromatolites grow much as they did billions of years ago. The Bahamas harbour stromatolites in certain lagoons. A few other sites around the world host small populations, but in the Proterozoic, before animals evolved, stromatolites were common, perhaps dominant in shallow marine environments, covering vast areas of seafloor and contributing significantly to global oxygen production. The structures fossilise readily. The layers of sediment and precipitated minerals harden into rock, limestone, dolomite, chert, and preserve the laminated structure with remarkable fidelity. When geologists find these rocks, they recognise the layering, the domed or columnar shape, the evidence of microbial origin. Stromatolites are some of the most distinctive fossils in the Precambrian rock record, some of the clearest evidence that life was present and active billions of years ago. They're not the only evidence, but they are among the most visible, the most intuitive, the easiest to identify even without a microscope. The cyanobacteria building stromatolites in the early Proterozoic are not fundamentally different from those in the Archean or those alive today. They are small, prokaryotic, lacking nuclei or complex internal structures. They photosynthesize using chlorophyll, fix carbon dioxide into organic molecules, release oxygen as waste. They divide by binary fission, reproduce asexually, form colonies held together by mucus and extracellular slime. Their morphology is simple: rods, spheres, chains of cells, and their biochemistry, while sophisticated, operates according to principles that have been conserved for billions of years. What has changed is not the cyanobacteria themselves, but the world around them. The oxygen they produce no longer reacts immediately with dissolved iron, because the iron is depleted. The oxygen no longer stays trapped in the ocean, because the sinks are exhausted. Instead, the oxygen escapes into the atmosphere, accumulates, transforms the chemistry of air and water and rock. The cyanobacteria are doing what they have always done, but the consequences are different now, planetary rather than local, irreversible rather than temporary. The stromatolites, in their slow growth, are witnesses to this transformation. The layers they build in the early Proterozoic are different from those in the Archean, different in mineralogy, in isotopic composition, in the trace elements they contain. The differences are subtle, visible only with careful analysis, but they record the changing chemistry of the ocean and atmosphere, the shift from a reducing world to an oxidizing one. The stromatolites are archives, storing information about the environment in which they grew, preserving it for billions of years in the only format that survives deep time: rock. Some stromatolites are associated with banded iron formations, growing in the same environments where iron was precipitating, contributing oxygen that drove the precipitation. Other stromatolites form in carbonate platforms, in settings where iron was absent or already oxidized, where the chemistry had moved past the iron buffering phase and into the oxygen accumulation phase. The distribution of stromatolite types, their mineralogy, their association with other rock types, all tell the story of a planet in transition, a planet where life is rewriting the rules of chemistry one microbial mat at a time. And the stromatolites continue to grow. They do not pause for the great oxidation event, do not slow during the Huronian glaciation, do not accelerate when oxygen rises or methane falls. They simply grow layer by layer at the pace dictated by sunlight and sediment and the biology of cyanobacteria. They're indifferent to the drama they enable, unaware of their role in planetary transformation. They build their domes and columns, trap their sediment, photosynthesize in the shallows, and the oxygen they release drifts upward into a sky that is learning slowly to hold it. The sulfur isotopes remember what the rocks cannot. They're preserved in ancient minerals, pyrite, barite, gypsum, locked into crystal lattices that survive metamorphism and burial, carrying information about the atmosphere in which they formed. The information is encoded in the ratios of sulfur's 4 stable isotopes, particularly in a phenomenon called mass-independent fractionation, which occurs only under specific atmospheric conditions. When scientists measure these ratios in rocks older than about 2.4 billion years, they find mass-independent fractionation. In rocks younger than that, the signal disappears. The transition marks the great oxidation event as clearly as any chemical signature can, a before and after written in isotopes. Mass-independent fractionation of sulfur isotopes occurs when ultraviolet radiation breaks apart sulfur dioxide molecules in the atmosphere. The UV photons have enough energy to split the molecule, and the way they split it depends on the isotope involved. Sulfur 32, sulfur 33, sulfur 34, or sulfur 36. In an atmosphere without oxygen, without an ozone layer to absorb UV, the radiation penetrates deeply and the fractionation is strong, creating isotopic signatures that deviate from the normal pattern expected from mass-dependent processes. The sulfur compounds that form sulfate aerosols, elemental sulfur, hydrogen sulfide, carry these anomalous isotope ratios, and when they settle out and are incorporated into minerals, the signal is preserved. After oxygen accumulates and the ozone layer forms, the UV flux at the surface drops. The photochemical reactions that produce mass-independent fractionation slow or stop. The sulfur isotopes begin to fractionate according to mass-dependent processes, equilibrium reactions, kinetic effects, which follow predictable patterns based on the masses of the isotopes. The anomalous signal disappears from the rock record, replaced by the normal, mass-dependent fractionation that characterizes modern sulfur chemistry. The transition is sharp, occurring over a geologically brief interval, and it provides one of the clearest markers of when oxygen rose to concentrations sufficient to form an ozone layer. The isotopes are measured with mass spectrometers, instruments capable of detecting differences in isotope ratios at the level of parts per thousand or smaller. The samples are prepared carefully, dissolved in acids, purified, converted to gases that can be ionized and measured. The process is slow, expensive, requiring samples from multiple locations and multiple stratigraphic levels to build a coherent picture. But the results are robust. Dozens of studies, using hundreds of samples from rocks around the world, confirm the pattern. Mass-independent fractionation before 2.4 billion years ago. Mass-dependent fractionation after. The transition is global, simultaneous within the resolution of radiometric dating, evidence that the change in atmospheric chemistry affected the entire planet at once. The sulfur itself comes from volcanic gases, primarily sulfur dioxide, released during eruptions and degassing events. The sulfur dioxide enters the atmosphere, reacts with water vapor to form sulfuric acid aerosols, or is reduced to hydrogen sulfide by microbial activity, or is oxidized to sulfate by oxygen if oxygen is present. Each of these pathways fractionates the isotopes differently, and the final isotopic composition of the minerals that form depends on the dominant pathway, on the atmospheric chemistry, on the availability of oxygen. Before the great oxidation event, the pathways favour mass-independent fractionation. After, they favour mass-dependent fractionation. The isotopes are a chemical clock, marking time by the presence or absence of oxygen, There are complications. Some processes can mimic mass-independent fractionation, or produce signals that are difficult to distinguish from it. Certain types of microbial metabolism, certain mineral precipitation pathways, can create isotopic anomalies that look superficially similar to mass-independent fractionation, but have different causes. Researchers must be careful to rule out these alternatives, to confirm that the signal they are measuring is truly atmospheric in origin, truly indicative of UV photochemistry in an oxygen-free atmosphere. The work is painstaking, requiring detailed knowledge of sulfur chemistry and careful interpretation of data that are often ambiguous or contradictory. But the overall pattern is clear. The isotopes record an atmosphere that lacked oxygen, that allowed UV radiation to penetrate to the surface, that processed sulfur through photochemical reactions that are no longer possible on Earth. They record a transition, abrupt on geological timescales, to an atmosphere with oxygen, with an ozone shield, with sulfur chemistry dominated by oxidation and reduction rather than photolysis. The isotopes are witnesses, silent and precise, preserving information that no other geochemical system can provide. The preservation of these isotopic signals is remarkable. The rocks that contain them have been buried, heated, deformed, sometimes metamorphosed at temperatures high enough to recrystallize the minerals, yet the isotope ratios survive, locked into the crystal structures, resistant to alteration as long as the minerals themselves remain intact. Some samples come from rocks that are 3 billion years old, among the oldest sedimentary rocks on the planet, and the isotopes are still there, still measurable, still telling their story. The sulfur isotopes also reveal details about the timing and pace of the Great Oxidation Event. The transition from mass-independent to mass-dependent fractionation is not instantaneous in the stratigraphic record. It occurs over a vertical interval of tens to hundreds of meters, depending on the location, which translates to millions of years in time. This suggests the oxygen rise was not a sudden spike but a gradual increase, possibly with fluctuations, possibly with reversals where oxygen dropped temporarily before rising again. The isotopes capture this complexity, recording a transition that is messy and prolonged, not the clean step change that simplified models might suggest. Other isotope systems provide complementary information. Chromium isotopes, for example, fractionate when chromium is oxidized and mobilized from rocks, a process that requires oxygen. The appearance of fractionated chromium isotopes in sediments is another marker of rising oxygen, independent of the sulfur signal. Molybdenum isotopes also shift when oxygen is present, because molybdenum is more soluble in oxidized water and its delivery to the ocean increases. Each isotope system is a different probe, measuring a different aspect of the changing chemistry, and together they build a more complete picture than any single system could provide alone. The sulfur isotopes, though, remain the most definitive. They are the clearest signal, the sharpest transition, the most direct evidence of atmospheric change. When a geologist wants to know whether a particular rock formed before or after the Great Oxidation Event, they measure the sulfur isotopes. If the isotopes show mass-independent fractionation, the rock is older than 2.4 billion years. If they show mass-dependent fractionation, the rock is younger. The method is not perfect. There are edge cases, uncertainties, debates about specific samples, but it is powerful, and it has revolutionized the study of Precambrian atmospheric evolution. The isotopes do not care about the debates. They record what happened, without interpretation, without bias. According to the laws of physics and chemistry, they are data, raw and unfiltered, waiting to be measured and understood. And what they reveal is a planet in transition, a sky that once allowed UV radiation to pour through unimpeded, and then, over millions of years, became filtered, shielded, transformed by the presence of oxygen and ozone. The isotopes remember, and in remembering, they allow humans, billions of years later, to reconstruct a moment in planetary history that left almost no other trace. The sulfur drifts through the atmosphere, reacts, settles into minerals, and the isotopes lock into place. The record is written, the memory is preserved, and the planet, moving forward, leaves behind a chemical signature that will endure as long as the rocks themselves. The sediments that turn to stone are red. They are deposited on land, in river channels and floodplains, in deltas where rivers meet the sea, and they carry the unmistakable colour of oxidized iron. The red comes from hematite, ferric oxide, rust in mineral form, coating the grains of sand and silt, staining the rock a colour that ranges from pale pink to deep crimson depending on the iron content and the size of the oxide particles. These are the red beds, and their appearance in the geological record is one of the clearest signs that oxygen has reached concentrations high enough to oxidize iron at the Earth's surface, in air rather than water, on land rather than in the ocean. Before the Great Oxidation Event, terrestrial sediments are grey or green, the colours of unoxidized minerals, of iron in its ferrous state, of a surface chemistry that is reducing rather than oxidizing. The iron in these sediments is present as ferrous silicates, as iron sulfides, as minerals that form in the absence of oxygen and remain stable as long as oxygen is absent. When these sediments are exposed to air, they do not rust. The iron stays reduced, the minerals stay grey, and the sediments, when they lithify, become grey sandstones and grey shales, rocks that preserve the chemistry of a world without oxygen. After the Great Oxidation Event, the chemistry changes. The iron in weathering rocks, in soils, in sediments being transported by rivers, encounters oxygen. The oxygen oxidizes the ferrous iron to ferric iron, which precipitates as hematite or goethite, coating the mineral grains in thin layers of rust. The sediments take on a reddish colour while they are still unconsolidated, while they are being transported or deposited, and they retain that colour when they harden into rock. The red beds appear in the stratigraphic record around 2.4 to 2.3 billion years ago, roughly coincident with the shift in sulfur isotopes, roughly coincident with the other markers of rising oxygen. The red beds are not uniformly distributed. They form primarily on land, in environments where sediments are exposed to air for long periods before being buried. River channels, floodplains, desert dunes, alluvial fans. These are the settings where red beds accumulate, where the oxidation of iron has time to occur before the sediments is covered by water or by more sediments. In marine environments, where sediments are deposited underwater and buried quickly, the red colour is less common, because the iron may not encounter enough oxygen to fully oxidize, or because organic matter in the sediments consumes the oxygen before it can react with the iron. The appearance of red beds does not mean the atmosphere is suddenly full of oxygen. The concentration required to oxidize iron at the surface is relatively low, perhaps 1% of modern levels, possibly less. Oxygen does not need to saturate the atmosphere to rust a riverbed. It only needs to be present, persistent, abundant enough that the iron encounters it during weathering or transport. The red beds are a threshold indicator, marking the point when oxygen becomes a permanent feature of the surface environment, when it stops being a transient local phenomenon and becomes a global constant. The colour of the red beds varies with the mineralogy. Hematite produces bright red, almost brick-like colour, the classic rust red visible in many Proterozoic sandstones. Goethite, a hydrated iron oxide, produces a more yellow or brown colour, softer and less vivid. The exact shade depends on the grain size of the oxide particles. Fine particles scatter light differently than coarse ones, and on the concentration of iron in the sediment. Not all post-GOE sediments are red, some remain grey, especially if they are deposited in anoxic environments or if they contain organic matter that reduces the iron after deposition. But red beds become common, widespread, a characteristic feature of terrestrial sediments in the Proterozoic and later. Geologists mapping ancient rock formations use the presence of red beds as a rough age indicator. If a sequence of sediments contains abundant red beds, it is likely younger than 2.3 billion years. If the sediments are grey or green throughout, with no red oxidation, they are likely older. The rule is not absolute. There are exceptions, ambiguities, local conditions that complicate the interpretation, but it is useful. A quick heuristic for placing rocks in the relative timeline of Earth history. The red beds are a visual marker, recognizable in the field, obvious even to non-specialists. The iron that oxidizes in the red beds comes from the weathering of igneous and metamorphic rocks on land. Rain falls on mountains, infiltrates cracks, reacts with minerals, dissolves iron and carries it away in solution. In the Archean, the iron stayed in solution, was transported to the ocean, contributed to the reservoir of dissolved ferrous iron that would eventually precipitate as banded iron formations. In the Proterozoic, after oxygen rises, the iron oxidizes during weathering or shortly after, precipitates as hematite, accumulates in soils and sediments. Less iron reaches the ocean in dissolved form. More iron is locked up on land, in red soils, in oxidized sediments, in rocks that will never reach the sea. The shift in iron transport has consequences for ocean chemistry. With less dissolved iron entering the ocean, the remaining reservoir is not replenished. The banded iron formations, which require abundant dissolved iron and a source of oxygen, become less common. The last major BIFs form around 1.8 billion years ago, and after that, the formations largely disappear from the geological record. There are minor resurgences, brief episodes when iron precipitates again. But the great age of banded iron formation is over. The ocean has transitioned to a state where iron is scarce, where oxygen is present, where the chemistry more closely resembles the modern ocean than the Archean one. The red beds also record climate, in tropical environments, where rainfall is high and weathering is intense. The red colour is often more pronounced because the iron has more opportunity to oxidize and the hematite particles are finer and more evenly distributed in arid environments, where weathering is slower and water is scarce. The red colour may be paler, and other minerals, gypsum, halite, may be more common. Geologists studying ancient climates look at the distribution of red beds, the associated minerals, the sedimentary structures, and infer the climate conditions under which the sediments were deposited. Some red beds are massive, homogeneous, showing little internal structure. These likely formed in environments where sedimentation was continuous and steady, where each layer was similar to the one before, accumulating without interruption. Other red beds are cross-bedded, showing the slanted layers characteristic of dunes or river channels, evidence of deposition by wind or flowing water. The sedimentary structures preserve information about the transport processes, the energy of the environment, the direction of currents or winds. The red colour is a chemical signature, but the structures are a physical one, and together they tell a more complete story. The red beds are also economically significant. Many are porous and permeable, capable of storing fluids, water, oil, gas, and they serve as aquifers or hydrocarbon reservoirs in many parts of the world. The iron oxide coating on the grains can reduce permeability in some cases, clogging pore spaces, but in other cases the red beds remain highly porous and are excellent reservoir rocks. Geologists drilling for water or oil pay attention to red beds, recognizing them as potential targets, understanding their properties and their place in the stratigraphic sequence. The appearance of red beds is not a sudden event but a gradual expansion. The earliest red beds are patchy, localized, restricted to certain settings or certain regions. Over time, they become more common, more widespread, until by the mid-Proterozoic they are a dominant component of terrestrial sedimentary sequences. The expansion tracks the rise of oxygen, the increasing oxidation of the surface, the slow transformation of the planet from a grey world to a red one. The change is visible from space, at least in principle, A shift in the colour of the land, from the dull tones of reduced minerals to the brighter hues of rust, and the sediments continue to accumulate, layer by layer, red upon red, staining the rock record with the signature of oxygen, marking the land as a place where iron rusts and the air has learned, finally, to carry the poison that will become breath. The timeline stretches, impossibly long, measured not in years or even millions of years, but in hundreds of millions. The Great Oxidation Event is not a moment but an era, a span of time so vast that mountain ranges rise and erode within it, that continents drift and collide, that entire cycles of glaciation and warming unfold. The oxygen concentration does not rise smoothly, linearly, in a simple upward trend. It rises, plateaus, falls, rises again. It fluctuates on timescales of millions to tens of millions of years, responding to changes in volcanic activity, in weathering rates, in biological productivity, in the burial of organic carbon. The atmosphere searches for equilibrium, overshoots, corrects, oscillates around a slowly rising mean. The period between about 2.4 and 2.0 billion years ago is sometimes called the Lomagundi event, named after a rock formation in Zimbabwe where the signature was first recognized. During this interval, carbon isotopes in carbonate rocks show pronounced excursion, a shift toward heavier values that indicates an increase in the burial of organic carbon. When organic carbon is buried, the carbon remaining in the ocean and atmosphere becomes enriched in the heavier isotope, carbon-13, and this enrichment is recorded in carbonates that precipitate from seawater. The Lomagundi event represents a period when organic carbon burial was unusually high, possibly driven by increased photosynthetic productivity, possibly by changes in ocean circulation or nutrient availability. The burial of organic carbon has a direct effect on atmospheric oxygen. Photosynthesis produces organic carbon and oxygen in roughly equal amounts, molecule for molecule. If the organic carbon is respired or decomposed, the oxygen is consumed again, and there is no net accumulation. But if the organic carbon is buried in sediments, locked away from the atmosphere, the oxygen remains. The burial of organic carbon is, in effect, a source of oxygen, and the Lomagundi event, with its elevated carbon burial rates, may have driven a pulse of oxygen accumulation that pushed the atmospheric concentration higher than before. The Lomagundi event lasts for more than 200 million years, one of the longest-lived geochemical anomalies in Earth history. During this time, oxygen may have reached concentrations approaching 10% of modern levels, possibly higher, though the estimates are uncertain and debated. The elevated oxygen would have expanded the range of aerobic life, allowed aerobic respiration to become more common, intensified the weathering of rocks on land. It would also have enhanced the oxidation of methane, reducing the greenhouse effect further, possibly contributing to the Huronian glaciations that overlap with this period. After the Lomagundi event, the carbon isotopes returned to more normal values, indicating that organic carbon burial decreased. The oxygen concentration likely fell as well, dropping from whatever peak it reached during the event. The drop may have been significant, possibly returning oxygen to trace levels, possibly creating a prolonged interval of low oxygen that persisted for hundreds of millions of years. This interval is sometimes called the boring billion, though that term more accurately applies to a later period, or the Proterozoic oxygen minimum, a time when oxygen was present but not abundant, when the atmosphere was transitional, neither fully reducing like the Archean nor fully oxidizing like the Phanerozoic. The fluctuations in oxygen are recorded in multiple geochemical proxies: iron speciation in shales, cerium anomalies in carbonates, trace metal abundances in sediments. Each proxy has its own strengths and weaknesses, its own sensitivities and ambiguities. Iron speciation, for example, can distinguish between anoxic and oxic conditions but does not provide precise oxygen concentrations. Cerium anomalies are sensitive to low oxygen levels but can be affected by factors other than atmospheric chemistry. Trace metals like molybdenum and uranium are mobilized by oxygen, and their concentrations in sediments reflect oxygen availability. But the relationship is complex and non-linear. Researchers studying this period must synthesize data from multiple proxies, multiple locations, multiple stratigraphic levels, building a composite picture that captures the overall trend while acknowledging the uncertainties. The picture that emerges is one of instability, of an atmosphere that is adjusting, reorganizing, searching for a new steady state. The instability persists for hundreds of millions of years, longer than the entire Phanerozoic, longer than the time from the Cambrian explosion to the present. The timescale is humbling, almost incomprehensible. A reminder that planetary transformations operate on scales that dwarf human experience. During this long transition, life continues to evolve. Eukaryotes appear, though the timing is uncertain, possibly as early as 2.1 billion years ago, possibly later. The eukaryotic cell, with its nucleus and membrane-bound organelles, is more complex than the prokaryotic cells that have dominated life until now. The origin of eukaryotes is tied to the rise of oxygen, because certain eukaryotic biochemistry, sterile synthesis for example, requires oxygen, but eukaryotes do not become dominant immediately. They remain rare, confined to specific environments, outnumbered by prokaryotes for more than 1 billion years. Their eventual diversification will reshape the biosphere, but that diversification is still far in the future. The continents during this period are small, scattered, not yet assembled into the large land masses that will characterize later eons. The largest is probably Knorrland, a supercontinent that forms around 2.7 billion years ago and begins to break apart around 2.5 billion years ago. The breakup of Knorrland may have influenced the Great Oxidation event, because rifting exposes fresh rock to weathering, consumes oxygen, and changes the balance between sources and sinks. After Knorrland, the continents drift, collide, form new configurations, Columbia, Rodinia, others whose names are tentative and whose reconstructions are uncertain. The tectonic cycles continue, unaffected by the changing atmosphere. Oceanic crust forms at mid-ocean ridges, ages, cools, and subducts back into the mantle. Continental crust thickens, is eroded, is buried, is uplifted again. Volcanic arcs form along subduction zones, releasing gases that influence atmospheric chemistry. The solid Earth and the atmosphere are coupled, interacting through weathering and volcanism, through the burial and exposure of rocks, through processes that operate on time scales of millions to hundreds of millions of years. The Great Oxidation event is a consequence of this coupling, a moment when the balance tipped and the atmosphere transitioned from one state to another. But the transition is not complete. Even at the end of the Great Oxidation event, even after oxygen has risen to measurable concentrations, the atmosphere is not like the modern one. The oxygen concentration is still low, perhaps 1 to 10% of modern levels. The deep ocean is still largely anoxic, with oxygen confined to the surface layers. Anaerobic life still dominates most ecosystems. The planet is intermediate, suspended between the reducing world of the Archean and the oxidizing world of the Phanerozoic, and it will remain in this intermediate state for another 1 billion years or more. The timeline stretches still, forward into the Mesoproterozoic, the Neoproterozoic, toward events that are still unimaginably distant. The snowball Earth glaciations of the late Proterozoic, the Cambrian explosion, the rise of animals. The Great Oxidation event is not the end of the story, but the beginning of a new chapter. The moment when the chemistry of the planet shifts and new possibilities open. The oxygen is in the air now, permanent and rising, and the Earth will never be the same. The planet turns. The cyanobacteria photosynthesize. The oxygen rises and falls and rises again. And the timeline stretches on, patient and vast, marking the slow transformation of a world, The silence after the storm is not silence, but continuation. The oxygen is in the atmosphere now. No longer a novelty. No longer poison to be endured, but a feature of the planet. A molecule woven into the chemistry of air and water and stone. The concentration stabilizes, not at modern levels, but at some fraction of them. Estimates suggest 10 to 40% of present atmospheric levels, though the exact value shifts over time, responding to the same forcings that have always governed atmospheric chemistry: volcanic outgassing, weathering, photosynthesis, the burial of organic carbon. The cycles continue, the feedbacks operate, and the oxygen finds its place within them. The ocean remains stratified. The surface layers, in contact with the atmosphere, hold oxygen at concentrations sufficient to support aerobic life. Cyanobacteria drift in the photic zone, forming blooms in nutrient-rich waters, building mats in shallow seas. Aerobic bacteria metabolize organic matter, recycling nutrients, consuming oxygen in the process. The upper ocean is oxic, or at least partially so, a thin layer where the new chemistry prevails. Below, in the deeper water, oxygen does not penetrate. The deep ocean is anoxic, possibly sulfidic, still dominated by the chemistry of the Archean. The boundary between oxic and anoxic water is called the chemocline, and it hovers somewhere in the mid-water column, fluctuating with season and location, a frontier between two worlds. The stratification persists for more than 1 billion years. It will not fully break down until the Neoproterozoic, when another series of environmental changes, possibly related to the breakup of the supercontinent Rodinia, possibly driven by changes in nutrient cycling or tectonic activity, pushes oxygen into the deep ocean and fully oxygenates the water column. But that transformation is still unimaginably distant, more than 1 billion years in the future. For now, the ocean is divided, its chemistry split between surface and depth, between the new world and the old. Life adapts to this divided ocean. Aerobic organisms colonize the oxic surface layer, exploiting the energy advantages of oxygen respiration. Anaerobic organisms persist in the anoxic depths, thriving in environments where oxygen never reaches. Continuing metabolisms that have operated since the Archean, the chemocline itself becomes a habitat, a narrow zone where both oxic and anoxic chemistries are available, where organisms can switch between aerobic and anaerobic metabolism depending on local conditions. The stratification creates ecological complexity, a vertical gradient of niches, a structure that will support greater biodiversity once more complex organisms evolve. On land, the surface continues to oxidize. Soils weather under an oxygen-rich atmosphere, releasing nutrients but also losing reduced minerals to oxidation. Rivers carry oxidized sediments to the sea, depositing red beds in deltas and coastal plains. The land itself takes on a different appearance, less grey, more red, stained with rust in a way that would be visible from orbit if any observer were present to see it. But there is no observer, no witness. The planet transforms itself in solitude, following the logic of chemistry and physics, indifferent to aesthetics or meaning. The rate of change slows, the great oxidation event, as a discrete transition, is over. The oxygen concentration has risen, the sinks have been filled, the chemistry has shifted. What remains is adjustment, the long process of equilibration as the planet settles into its new state. The atmosphere will fluctuate, oxygen rising during periods of high organic carbon burial, falling when burial rates decline, but the fluctuations are smaller now, less dramatic, oscillations around a mean rather than wild swings between extremes. The planet has found a rough equilibrium, not stable but persistent, a state that will last for hundreds of millions of years before the next major transition. The stromatolites continue to grow, indifferent as always. They are less common now than they were in the Archean, possibly because grazers are beginning to evolve. microscopic eukaryotes that consume the microbial mats before they can build large structures, or possibly because environmental conditions have shifted in ways that favour other types of photosynthetic communities. But they are still present, still building their layered domes in shallow water, still contributing oxygen to the atmosphere. Their growth is slow, the contribution modest on a planetary scale, but persistent, cumulative. Part of the larger system, the banded iron formations have ceased. The ocean no longer holds the dissolved iron necessary to form them, and the few episodes of iron precipitation that occur after the GOE are minor, localized, brief. The great era of BIF formation is over, and the formations that exist, vast, thick, covering areas the size of modern countries, are relics now, evidence of a chemistry that no longer operates. In billions of years, humans will mine these formations, extract the iron, smelt it into steel, build cities and machines from the rust that fell in an ancient ocean. But that is unimaginably distant, irrelevant to the present. The carbon cycle is reorganized. With oxygen in the atmosphere, organic matter oxidizes more readily, both through aerobic respiration and through abiotic reactions with oxygen in the environment. This increases the turnover rate of carbon, reduces the accumulation of organic-rich sediments, shifts the balance between photosynthesis and respiration. The burial of organic carbon still occurs. It must, to maintain oxygen levels. But the efficiency changes. The locations change. The types of sediments that accumulate change. The cycle is faster, more dynamic, more responsive to environmental perturbations. The nitrogen cycle, too, has shifted. Nitrogen fixation, the process by which certain microbes convert atmospheric nitrogen into ammonia, has been operating since the Archaeon. But denitrification, the reverse process, where nitrate is reduced back to nitrogen gas, becomes more important after oxygen rises. Because the enzymes involved in denitrification require oxygen or oxidized forms of nitrogen, the nitrogen cycle becomes more complex, more interconnected with the oxygen and carbon cycles, a web of chemical transformations that link the biosphere to the atmosphere. The planet is quieter now, in a sense. The drama of the great oxidation event, the rising oxygen, the falling methane, the glaciations, the extinctions, has subsided. What remains is the slow grind of geological and biological processes, operating at their usual pace, no faster or slower than before. The oxygen is simply there, a background condition, a constant rather than a variable. It is no longer changing the world, it has already changed it. The sky holds its oxygen, a few percent by volume, enough to rust iron, enough to filter UV, enough to support aerobic life. The concentration will vary over the next billion years, rising and falling with the cycles of carbon burial and volcanic activity, but it will not drop to zero again. The transition is irreversible, at least on timescales that matter to the planet's remaining lifespan. The reducing atmosphere of the Archean is gone, replaced by an oxidizing atmosphere that will persist until the sun expands and the oceans boil away billions of years hence. And so, the planet turns, carrying its oxygen, its stratified ocean, its red soils and oxic surface waters. The cyanobacteria photosynthesize, the aerobic bacteria respire, the continents drift, the climate oscillates, the cycles continue. The great oxidation event is over, fading into deep time, leaving behind a planet transformed, a chemistry rewritten, an atmosphere that holds, finally, the molecule that will one day be called breath. The silence is not empty. It is full of continuation, of processes ongoing, of a world that had learned to live with the poison it created. And the oxygen drifts through the air, molecule by molecule, patient and persistent, waiting for the next transformation, the next threshold, the next slow revolution that will take another billion years to unfold.